Hi folks, today we're going to be going over the 55s. You're going to need your calculator and your cover out. The first thing that I want to introduce you to is this thing that's called autoionization. That's where water molecules will actually form this item that's called a hydronium ion and called hydroxide. This doesn't occur very often. Only about 1 in 100 million water molecules does this occur, but it shows that a little bit of acid, a little bit of base can form, but when the hydronium ion and the hydroxide ion combine together, they're going to make water molecules. So it doesn't happen a lot, but it does occur. So the equation can be simplified if we emit the water molecule. And so what we end up getting is we get H2O. And again, that's a liquid. And we put a double arrow there, meaning this reaction can go both ways. And you end up getting the hydrogen ion, aqueous, and you end up getting the hydroxide ion, aqueous. So what we kind of did is we just chopped off this extra OH that's here and just left the hydrogen ion. And we have the hydroxide ion, and we cut out one of the water molecules and we simplified it. And that's our reaction for acid-base reactions that we've been using for a long time. But that's going to come into play on the next slide. So on this next slide, we have to do a couple things, and the thing that we have to do that's new is this K value. K value states which way a reaction is going to go. Are we going to have a reaction that's going to go back towards the reactants, or are we going to have a reaction that's going to go more towards the products? So that K value comes in. We talked about strong and weak bases, how much an acid or a base will break apart, and the K value is involved with that. So it says numbers that are less than 1 favor the reactants. So if you have a K value that's smaller than 1, that means the arrow is going to be going back towards the reactants, and only a little bit of the product is made. So our weak acids and our weak bases, those would have K values that are very small. And our strong acids and bases, they would have K values that are very large, greater than 1. So in this problem, we need to write the K value for this reaction right here. There's a couple things that we need to know. Solids and liquids are not involved in our K reactions since their molarities never change. So if I'm going to write the reaction here, we have K, and this is going to be for water. It's going to be equal to our products over our reactants. And this bracket means molarity or concentration. So I put the hydrogen ion in there like that. And I close it up. So that's the molarity or the concentration of our hydrogen ions. And then I do the exact same thing for our hydroxide ions. And I leave out this water, which is a liquid. They're just never included in K reactions. So that is our K value for a water molecule, an acid-base reaction. And that is kind of stated right down here. And the K value for that is this number right here, and which is an extremely small number, meaning that this reaction does not occur a lot where the water molecule breaks apart into hydrogen ions and hydroxide ions. We're going to use this red part, this part right down here, in some mathematical reactions as we're going along. If you're a little confused right now, don't worry, it'll clear up as we're going along. So in pure water, or when a solution is neutral, what must be true of the molarity of the hydrogen ions and the molarity of the hydroxide ions? So again, when it's neutral, what must be true of those two concentrations? Well, what must be true of those two concentrations is they must be equal to each other. If it's neutral, all the hydrogen ions have to react with their hydroxide ions and make water. So neutral reactions, you must have equal molarity for hydrogen ion and equal molarity for hydroxide ion. In a basic solution, would the hydrogen ion concentration equal the hydroxide ion concentration? The answer is no. If it's basic, you better have more of the hydroxide ion concentration. The molarity of the hydroxide ion must be higher than that of the hydrogen ion. Otherwise, it's not a basic solution. And I think we skipped a slide. I'll go back one. Nope, I guess we got that. Oh, we forgot to answer number 5. Sorry about that. In an acidic solution, would the hydrogen ion be equal to that of the hydroxide ion? Well, if it's acidic, it better have more of these hydrogen ions available. So, in an acidic solution, would the hydrogen ion equal the hydroxide ion? No, it would not. You better have more hydrogen ion if it's an acidic solution. Sorry about the mix-up of 5 and 6 there, folks. So on to number 7. Water at 25 degrees Celsius, roughly room temperature. It turns out that the hydroxide ion concentration is this number right here. What is the value for the hydrogen ion concentration? Well, we're going to use this math that's right at the bottom of this chart. It's on your cover. It's also on this worksheet. So we know that the hydrogen ion concentration and the hydroxide ion concentration equal 1.00 times 10 to the negative 14th. So we just do some algebra. If we know the hydroxide ion concentration is 1.00 times 10 to the negative 7th, and the hydrogen ion will still be over here. We do a little algebra. Where you leave the hydrogen ion on that side, you divide this side by the 1.00 times 10 to the negative 7th. You divide this side by the 1.00 times 10 to the negative 7th. And you end up getting your hydrogen ion concentration equal to 1.00 times 10 to the negative 7. Now, on your calculators, it might give you a whole bunch of zeros and then a 1. So a really small decimal. If you want to fix that, and you might want to do that for this unit, you might want to do what it says right there. Hit the second button, and then the Science/English button to get scientific notation on your Texas Instrument calculators. It's right in the upper left-hand corner. It's right next to the second button. If you do that, it'll start giving you numbers in scientific notation, and that's going to come in handy in this unit. Number 8, if the solution had a hydrogen ion concentration of this, what would be the hydroxide ion concentration? Why don't you try to do the math of this? Pause the program, see if you can do it, and then check your answers. So again, coming back, this is our formula right here. It's got to equal 1 times 10 to the negative 14th. So I know that this is my formula. I know my hydrogen ion concentration is 1.00 times 10 to the negative 6th. My hydroxide ion concentration, I don't know. It's all got to total up to 1.00 times 10 to the negative 14th. I do some algebra, and what I end up getting at the end is my hydrogen ion concentration is equal to 1.00 times 10 to the negative 8. Again, I use this formula right down here. I did some algebra, and I solved for that value. Number 9, if a solution had a hydroxide ion concentration of 1 times 10 to the negative 4th, what would be the hydrogen ion concentration? Pause the program, see if you can do the math. If you do the math correctly on this one, your hydrogen ion concentration is going to end up equaling 1.00 times 10. Start that over again, 1.00 times 10 to the negative 10th. You did your math correctly. Again, just using algebra to solve for x. What is pH a measure of? It's a measure of this right here, your hydrogen ion concentration, or the molarity of your hydrogen ions. So what's pOH stand for? Well, it stands for your hydroxide ion concentration. In other words, how many hydroxide ions do you actually have? 12. What is the pH of a neutral solution? 7, or 7.00 repeating. And what of that of a pOH? If a neutral solution, that'd be 7.0 repeating. So what is pH plus pOH? We're going to use this formula right on top that I have in red. So if I know the pH, I can solve for pOH. If I know the pOH, I can solve for the pH. So what is pH plus pOH? It is equal to 14.0, according to that little chunk on your cover. So what would be the pOH of a solution if the pH was 6? Well, pH is 6 plus a pOH, so pOH, and that equals 14.0. Well, if I want to find the pOH, I subtract 6 from this side, subtract 6 from this side, and I get my pOH equal to 8.0. So I'm just using this equation up on top. What would be the pH of a solution at a pOH of 8.5? You should definitely try to solve this problem, folks. pH plus 8.50 equals 14.0. So I do the math on that, and I get my pH to equal 4.5. That would be with the correct sig figs. I know it says to go to 3 sig figs. Then we go there, but really the answer should be 4.5. 16. In most solutions of weak acids and bases, like these two, these are a weak acid and weak base, the concentrations of the hydrogen ion and hydroxide ion are very small. That means their K values would be very small. To allow for the easy comparison of small values of hydrogen ion, a logarithmic scale was developed, called the pH scale. pH stands for potential hydrogen. Well, folks, I'm sorry if your screen got a little bouncy on you. We had a couple technical difficulties. For number 17, for example, if the hydrogen ion is equal to the -4th, the pH would refer to the exponent. So the pH, as long as there's a 1.00 out in front, this exponent actually tells you the pH. So the pH here is equal to 4. Now, I know this isn't on your sheet, but let's say the hydrogen ion concentration is 9.00 times 10 to the -4. This -4 tells us that our pH should be around 4. When we do the math, and I'll teach you how to do the math shortly, when we do the math, we actually get 3.05. So this exponent gives us a ballpark of where we should actually be for pH. On this problem, our exponent is to the -5th, so that means our pH would be equal to 5, as long as there's 1.00 out in front. Again, I know this isn't on your paper, but if we were to do the same thing using the math down here, we find out that we have an exponent to the -5, which means our pH should be around 5. When we do the actual math that's over here, we get 4.05. So the exponent gives you an idea of what your pH should be. So what I'm going to ask you to do right now is you're going to close this video up. I have another video that comes right after this. I only have 15 minutes to time, and it's going to take me about 10 more minutes to teaching the actual mathematics of how to use this chart and to how to use your calculator. So, see you in a bit.